10th International Physics Olympiad, year 1977, IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. Message me if interested. My email is fred1996@hotmail.com, or you can use Skype name Eduard F. 1996. Problem number 1. Compression ratio of a 4-stroke internal combustion engine is epsilon equal 9.5. The engine draws in air and gaseous fuel at a temperature 27 degrees Celsius at a pressure 1 atmosphere equal 100 kilopascal. Compression follows an adiabatic process from point 1 to point 2. See figure 1. The pressure in the cylinder is doubled during the mixture ignition process 2 to 3. The hot exhaust gas expands adiabatically to the volume 1/2, pushing the piston downwards, process 3-4. Then the exhaust valve opens and the pressure gets back to the initial value of 1 atmosphere. All processes in the cylinder are supposed to be ideal. The Poisson constant means the ratio of specific heat Cp over Cv for the mixture, and the exhaust gas is gamma equal 1.40. The compression ratio is the ratio of the volume of the cylinder when the piston is at the bottom to the volume when the piston is at the top. Question A. Which processes run between the points 0 to 1, 2 to 3, 4 to 1, 1 to 0? Question B. Determine the pressure and the temperature in the states 1, 2, 3, and 4. Question C. Find the thermal efficiency of the cycle. Question D. Discuss obtained results. Are they realistic? Solution for problem number 1. Question A. Which processes run between the points 0, 1, 2, 3, 4, 1, 1, 0? Solution. First, we have process 0, 1. It is an intact stroke, and it is isobaric expansion and the isothermal process. Next one, 1, 2. Compression of the mixture. This is adiabatic compression. Number 2, 3. Mixture ignition. This is isochoric process. Next one, 3, 4. Expansion of the exhaust gas. This is adiabatic expansion. Next one is 4, 1. Exhaust. This is isochoric process. And last one is 1, 0. Exhaust adiabatic process. This is adiabatic compression. So that was a solution for the question A. Question B. Determine the pressure and the temperature in the states 1, 2, 3, and 4. Solution. Let us denote the initial volume of the cylinder before induction at the point 0 by V1 and after induction at the point 1 by V2, and the temperatures at the particular points by T0, T1, T2, T3, and T4, and the pressures are P0 equal P1, P2, P3, and P4. The equations for particular processes are as follows. Process 01. The fuel-air mixture is drawn into a cylinder at the temperature T0 equal T1 equal 300 Kelvin and the pressure of P0 equal P1 equal 0.10 megapascal. For the process 1-2, since the compression is very fast, one can suppose the process to be adiabatic. Hence, we have P1 V2 power mil equal P2 V1 power mil, and the P1 V2 over T1 equal P2 V1 over T2. And from the first equation, one obtains P2 equal P1 multiplied by V2 over V1 power mil, or P1 epsilon power mil. After that, by dividing this equation by this equation, we arrive after the straightforward calculation at T1 V2 power mil minus 1 equals T2 V1 power mil minus 1, and finally T2 equal T1 V2 over V1 power mil minus 1, or T1 epsilon power mil minus 1. For given values, mil equal 1.4, epsilon equal 9.5, P1 equal 0.10 megapascal, T1 equal 300 Kelvin, we have T2 equal 2.34 megapascal and the T2 equal 738 Kelvin. For process 2-3, because the process is isochoric and the P3 equal to P2, we have next calculations. T3 over T2 equal T3 over T2, so T3 equal T2 multiplied by P3 over P2, or 2 times T2, or 1476 Kelvin, and the P3 equal 4.68 megapascal. For process 3-4, we have the expansion is adiabatic, therefore we have equations similar to equations for process 1-2. So it means that P3 V1 power mil equal P4 V2 power mil, and P3 V1 over T3 equal P4 V2 over T4. From the first we have P4 equal this expression, and which is P3 epsilon power negative mil, and if we remember that P3 equal 2 P2, so it means that finally P4 equal 2 P1. And the same thing for temperature. First we have to divide this equation by this equation and get this expression. After that we can find that temperature T4 equal this expression, or T3 multiplied by epsilon power 1 minus mil, but T3 equal 2 T2, so it means that finally we have T4 equal 2 multiplied by T2. Numerically we will get P4 equal 0.2 megapascal and the temperature T4 equal 600 Kelvin. For the final isochoric process 4-1, we have T4 over T1 equal T4 over T prime 1. So it means that T prime 1 equal T4 multiplied by T1 over T4, or T4 over 2, or initial 300 Kelvin, which is T1. So finally we got all numbers for all points. for T and P. That was a solution for question B. Question C. Find the thermal efficiency of the cycle. Solution. Thermal efficiency of the engine is defined as the proportion of the heat supplied that is converted to net work. The exhaust gas does work on the piston during the expansion 3-4. On the other hand, the work is done on the mixture during the compression 1-2. No work done by the gas during the process 2-3 and 4-1. The heat is supplied to the gas only during the process 2-3. The net work done by 1 mole of the gas is W12 plus W34, which is this expression. Also, we have heat supplied to the gas is Q23, which is CV multiplied by T3 minus T2. Also, we have gamma equal Cp over Cv. It means that Cv equal R over gamma minus 1. Hence, we have for thermal efficiency nu equal W over Q23, or after some sort of calculations we will get 1 minus epsilon power 1 minus gamma, which is about 59.3%. And that was a solution for question C. And the last question D. Discuss obtained results. Are they realistic? Solution. Actually, the real PV diagram of the cycle is smooth, without the sharp angles. Since the gas is not ideal, the real efficiency would be lower than the calculated one. That was a solution for the last question D, and here we solve all questions for problem number 1.